Up next, we have Thomas Hunter II. He is the author of Distributed Systems with Node.js. He is the co-author of Multi-Threaded JavaScript. These are both O'Reilly books, right? He is an organizer of Node School San Francisco. He has contributed to dozens of enterprise Node.js services and has both of the OpenJS Node.js certifications. Please welcome to the stage, Thomas Hunter.
Thanks for that. Cool. All right, welcome to my talk. The title of this is obviously Node.js Package Management. Of course, I'm Thomas Hunter. And the content from today's talk is based on a book of mine, Distributed Systems with Node. And if you actually snag me after this talk and ask me really cool questions, I brought 2 physical copies with me that I'm going to give away today. If you'd like more information about this book, you can hit it up at that bit.ly link, and I'll throw a link at the end of the presentation as well. All right, in this talk, I'm going to, go over a few different topics or chapters. First, we're going to look at the basics of package management in Node. Next, we're going to look at the dependency tree. After that will be how module resolution works. And then finally, we'll cover some best practices. Woo! Thanks. So first, basics, how do dependencies work? Well, actually, let's first define some terms. It's actually confusing, a lot of these terms, and I actually got it wrong for about the first 5 years of my Node career. So first, a module is a file that you can require or even import, and that sits on disk and contains some sort of semblance of code. A package is an archive of modules and their related supporting files. And those ultimately get tarballed, combined into a tar package, and then uploaded. So a dependency is a package within the context of an application, and that the application depends on that package. And so a package makes it easy to distribute different modules. And so packages ideally should be beneficial to more than one application. If you've got a bunch of applications that are highly specific to just your app, don't bother making a package from it. Just keep them as separate modules. These packages are ultimately hosted on npmjs.com. Even if you're using the Yarn package manager, I believe they sort of rely on npmjs as the sort of source of truth. Though things like probably the GitHub packages might sort of upset this in the future, especially since GitHub had acquired npm. And fun fact, while I did some research at the Intrinsic company, which was a Node security company, we sort of realized that most of our customer applications, more than 95% of their code, and in most cases 99%, was actually code that was lived inside of dependencies instead of the actual application code. And so if you're curious, you could actually run this command inside of one of your applications and then see the breakdown for yourself. So dependency installation, most of us here have installed dependencies. I'll just sort of run through this. So ultimately, dependencies are listed inside your package.json file. There's several different CLI tools that you can use to manage these packages. And so npm, of course, is the most popular and ships with Node. Yarn is actually, I suppose the two of them compete in popularity, especially depending on the year. pnpm is another fun one, which we'll also take a peek at as well. Fun fact, though, the latest version of Node ships with an executable called CorePack. And so CorePack, it's essentially a wrapper that makes it easier to work with pnpm and Yarn. Doesn't really do too much with npm itself. But if you have at least Node.js version 16.9, you'd have this CorePack available to you. And it makes it easy to sort of download and execute these other package managers, similar to the NVM Node Version Manager utility if you've used that in the past. Applications have both dependencies and dev dependencies. And so dev dependencies are those that really are only needed for development, for perhaps building or running tests. But then you also have the normal dependencies. So by default, if you run like npm install, you're going to get the whole lot. But if you provide the production flag, you're just going to get the pure dependencies. The other package managers have equivalents. In fact, some package managers are made with production in mind, or running in CI, and it will actually won't ever install dev dependencies. Some of the more obscure ones. These dependencies, they end up getting extracted to the node modules directory. And there's actually a bit of non-determinism involved when you perform an installation. So there's a way around this. You can sort of disable some of these scripts, but by default, you're running install scripts. Perhaps you're compiling Node native modules. In some cases, you're actually downloading a massive binary from the internet. So the Phantom.js, for example, I don't know if it still does, but for a long time, it would actually download a huge binary from the internet. So all this to say that when you perform an installation, you don't necessarily get a deterministic file system by the time you're done. And just some quick commands that we're probably all familiar with. If you run npm init, you're going to get a package.json. You're going to get a node modules directory. If you install a file, at that point, you're going to get a package installed within that node modules directory. Packages are versioned, and ideally, they follow SemVer, which stands for semantic versioning. And so this is that 3-number version that we end up seeing everywhere. And so these numbers stand for major.minor.patch. It's actually a common misconception that major correlates with a breaking change, minor correlates with a feature change, and bug fix correlates with a patch change. That's actually only true, for example, in the case here, where we have the leading number is not 0, but in the cases where the leading number is 0, sort of the definition of these ends up shifting. And so SemVer is really useful because when we install packages, we don't necessarily have to install an exact version, which is shown in the first row here, but instead we can actually use these different symbols to say that we want a different range of packages. So if we use the exact string, for example, 1.2.3, we're only going to end up with version 1.2.3 of the package. Now with the bug fix, if we use the tilde operator at the beginning of our version, we'll end up installing a package, but we'll only receive patch updates. Actually, I have a typo here. It says that's the npm default. The third line is actually the default with npm. And so when you run like npm install foo 1.2.3, you would then get caret 1.2.3 inside of your package.json file. And so the final one represents new features only. That uses the caret. That's the default with npm. And so that's saying, essentially, as long as the package works and is compatible, feel free to install those updates. And yeah, that ends up being the default. There's also other ranges that we can use as well. You might have seen like the greater than, less than, equal signs. But these symbols here are usually the most common. All right, so now let's look at the dependency tree. Where do these dependencies actually go once we install them? Well, there's actually a few ways to consider the dependency tree. The first one is what I like to call the logical dependency tree. And so this dependency tree is essentially a hierarchy that sort of perfectly resembles the dependencies of your application. So in this case, we have our application version 1.0. It depends on QS and PG and Express. And then Express depends on QS and content type. So in this case, we have 3 dependencies, QS, PG, and Express. And then we also have what we can refer to as transitive dependencies or sub-dependencies, and that would be the other QS and content type. And so how might we sort of represent this tree on disk? Well, first, we can look at this sort of naive approach. With this approach, the file system ends up perfectly resembling the logical tree. So in this case, we have our app directory, and that contains the node modules directory. Inside of that is a QS, PG, and Express directory, but then Express itself has modules that it depends on. And so we have a node modules directory inside of that, as well as the QS and content type, packages in that directory as well. But this is not completely ideal because we see that the QS package is repeated multiple times, whereas it doesn't necessarily need to. And that can result in a higher disk size. But there's also a pretty big flaw here in that if we had a cyclical dependency relationship, we'd actually end up with a file system that is perhaps infinitely nested. So if content type depended on Express for whatever reason, you just get deeper and deeper and deeper, and you'd run out of disk space. And so we can improve on this a little bit. And this is essentially what the package managers npm and yarn end up doing. So in this case, the modules, they end up getting sort of like hoisted up or deduplicated on disk. And so in this case, the layout looks pretty similar to before. However, we see that the QS module has been hoisted up from instead of being inside the Express module to only existing at the top level. And so when the Express package ends up requiring the QS package, I've been using the term wrong. These are all packages, not modules. And so when it requires that, it actually requires it as a sibling. But then we can actually go even further, and the content type package can also be hoisted up to the root as well. And so when you do that, we end up with a disk size that's a bit smaller. And that's beneficial for deploying applications, for example. Determining this physical tree isn't always completely straightforward. There's a bit of complexity involved. So we can consider one situation that's fairly straightforward. In this case, the application depends on the foo package and the bar package. Both of those depend on the QS package. And they're both using a compatible SemVer range. So both of them saying they want at least 5.1.2 or 5.1.4. And they're willing to get newer patch versions of this package. And so in this case, QS 5.1.9 is installed and then hoisted to the root. And so that one's pretty straightforward. However, sometimes there are incompatible versions. And so in the case that we have a foo and a bar package that both depend on QS, but in this case they depend on an incompatible version, one depending on version 5, one depending on version 6. In that case, only one of them can get hoisted up. So perhaps we would then hoist the one that's like maybe the higher version, or you could imagine some algorithm sort of deciding the hoisting rules for that. In this case, the QS module, the other one, ends up sitting still as a child package of the package that depends on it. But there's other situations as well that are even more interesting. You could have multiple versions of the exact same QS, 5.1.2 on disk that are unable to get hoisted because other packages need to hoist a different version. And so with this approach, you still end up with some disk redundancies, especially with larger, complex projects. There's actually another approach, though, that's quite interesting is what pnpm does. And so the pnpm package manager uses symlinks. And so what it does is it still uses the Node modules directory, because that's something built into Node. It understands the Node modules directory. But also creates a .pnpm directory inside of that. And so the way it works is if you install a package, for example, foo, you'll end up getting a foo directory inside the Node modules directory. But that directory is a symlink to a different one. And the one that it symlinks to is a folder called the name of the package, and then the @ symbol and the version that sits inside that pnpm folder. And then inside of there, you get a Node modules directory and a foo directory as well. And then the foo package, any dependencies that have, ends up getting symlinked within the Node modules directory for that package. And so if foo depends on bar, you might see that there's a .pnpm/bar, and then a version for that, which is pointed to in the foo package's Node module. And so that's interesting because we're then able to install a single version of every single package, and we just throw them all in that pnpm directory, and that's the only physical space that they consume. Otherwise, we're dealing with a bunch of symlinks that point to them. And so that both reduces in minimal disk usage, but you're also able to put many different sibling foo directories, foo package directories in the same pnpm directory. Otherwise, if you're just using the name, you would lose that version information and you would have collisions. So concerning install determinism, each time, at least in the past, this is the way it used to work. How many people here have been using Node for maybe more than 5, 6 years? Okay, I think we're a dying breed. So this is more of a war story, perhaps. It used to be that we didn't have any sort of lock file, and you would run npm install, and every single time you ran it, you might get a different version of packages installed. We would actually see bugs where our colleagues would run npm install, and they'd get different files. The reason for this is that package maintainers constantly release new packages, new versions, updating them, and then with the SemVer ranges, you end up getting different versions of packages. Those might have different sub-dependencies, and your tree could change every time. Luckily now, the npm CLI, it supports a package lock JSON. Its older brethren was I believe the npm shrink lock JSON file. And I believe ultimately they were inspired perhaps by Yarn's yarn.lock YAML file. And so this file ends up enforcing exact dependency hierarchy. And so regardless of what happens with packages changing, you would still get the same npm installation. You'd still get the same package hierarchy. So when you actually install these things, if you run the npm outdated command a bunch of times, you will see that your application does end up having outdated packages. And that's something that wouldn't necessarily happen before the shrink the lock files became popular. And so also remember that due to the non-determinism of installs, downloading files, compiling native modules, you don't necessarily end up with a 100% deterministic file system, even with lock files, especially if you have a more complicated app with more complicated dependencies. All right, so module resolution. So how does the require call work? Or to an extent, how does the import statement work as well? And so just a bit of an overview of require. The way it works is you call the require function, you pass in an argument to it, which is like some sort of semblance of a module or package that you want to require. So if that string that you pass in starts with a period or a slash, it's going to look for a module. And again, the module is just a file on disk. And this is true with import as well. One thing to keep in mind is that global packages aren't readily requireable. So if you do like an npm install -g, you can't simply require that package. Though you could if you had an absolute path to the location where that package sits on disk. And then if you end up specifying something that doesn't start with a dot or a slash, it's going to assume you're looking for a package. So it's going to look for that in like the node modules directory. So the way it works is it consults the node modules directory of the current file. And if it doesn't exist in there, it's going to go up a directory, check that for node modules. It's going to continue to ascend until it reaches the root. When you do end up requiring a file, the absolute path to that file as it sits on disk is used as the key in something called the require cache, which we'll look at in a moment. And so that's why if you build out an application and you have like a file that contains like a singleton database connection that it exports, if you require that from file A.js and file B.js, in either case, you're still going to end up with the same file, the same singleton instance. And so yeah, all this stuff requires a module resolution algorithm, which is just a fancy way of saying it's a bit complex. There's a few hoops that we have to jump through. So let's look at some examples of how this stuff works. The module resolution algorithm, it's actually like a couple pages for the require call, and then it's like, I don't know, maybe several pages for the import. But here we're just going to look at some high-level examples. And so all these examples assume that we're calling the code from a folder, from the SRV folder in the root, and we're just calling it from the file. The file doesn't matter, but we'll just call it server.js. So in the case where we require URL, that ends up being the core URL module that's baked into the node itself. And so when you require URL, it's just going to short circuit that, see that it's built in, and then return the built-in module. If you require /module, in that case, it's a relative path to the module, and it's just going to require the module.js in the current directory. If we require left pad, it's going to assume that's a package, and so it's going to look in the left pad directory within the current node modules directory. And then if it's not in there, it's going to look in the node modules directory at the root of the disk, which is one level up. And then now that we've reached the root, it's exhausted it. And at that point, it would give up if it didn't find it. Then after that, require foo.js. It sort of looks different. It looks like we're trying to require a file on disk. And I'm sure I've made this mistake a few times, and I'm sure a few of us have as well. But that doesn't not actually require foo.js locally. It does not require the module relative to the current module. Instead, it requires the package. And finally, if you call require./foo, you actually end up with a bunch of fun possible outcomes. And so if you require ./foo, the first thing it's going to look for is the foo.js file in the current directory. If it doesn't find that, it's going to look for foo.json, foo.node, a native module. If it's not in there, it's going to look for an index.js file in a foo directory, index.json in a foo directory. And so, there's just a bunch of hoops that it's going to jump through. There's a bunch of disk access that it's going to make. Also keep in mind that these require calls, they're synchronous blocking calls. Probably the performance isn't too high unless you're sort of dynamically calling these require statements. And so these rules, they apply for the most part for the import statement as well, except for the sort of the ambiguity with regards to file extensions at the last example. That one doesn't apply, probably because import is like inspired from the browser, and your browser's not going to make 50 requests to the server trying to find the file that it wants to get. Instead, you have to be a bit more explicit with the file extensions. I apologize for the text. It's a little small, but I'll try to explain it. This is what the require cache looks like. And there's probably an import equivalent. I just haven't looked into it yet. But this object is available at require.cache and requires, available in all your JavaScript files, your non-ESM JavaScript files in Node. And so this is that sort of key value structure I was talking about, where the key is the absolute path to the module on disk, and then the value is an instance of this module class, which contains a bunch of information about the module. So the most interesting things here, I think, is one, we have the paths array, and that tells you all the different locations where it's going to look for the node modules and sort of ascend until it reaches the root. And so in that array there, you can sort of see it's looking for node modules in the current directory, and it goes all the way up. Another thing that's interesting is the exports object. And so in this case, this module actually isn't exporting anything, but that would contain the actual object that you're assigning to the exports object. So that's sort of interesting because sort of globally within your Node application, you can sort of get access to any of the exported objects anywhere else within the application if you wanted to. Another thing interesting is that loaded flag, and that tells you if the file has completed loading at that point in time. And so if it's false, then you wouldn't have any access to the exports anyway. Like it would still perhaps be synchronously exporting that code. Cool, let's look at some best practices. What's the best way to use all this stuff? Well, with regards to deployment and workflow, you should probably periodically run the npm outdated command. And that's going to tell you any packages that happen to be old. Theoretically, authors are constantly improving packages, maybe even adding features or making it more performant, fixing vulnerabilities. And so in that case, probably every few months, sort of depending on the side of the project, you'd probably want to keep that up to date. I've worked at companies, that sort of left these outdated for several years, and it ends up being sort of a nightmare to update them all at once. So certainly take the time to attack that tech debt. A bit more serious version of npm outdated, though, is the npm audit. So you run that command, and it's going to list packages that have known vulnerabilities. Of course, ideally, the author of a package isn't releasing a package with known vulnerabilities. It's sort of something you find in the future, and then we sort of know about it in retrospect. And so running npm audit will actually compare the list of packages that you have installed to a database of known vulnerabilities, and if it finds them, it will tell you about it. And if you're lucky, there's a fix available for it. Another tool I really like is dep-check. And so this is a package that's maintained by some third party, but you can just run npx to execute the package as if it were installed globally. And so what that does is it'll find orphaned packages. And so you can run this within your project, and it will compare the dependencies that you have in your package.json. It will then sort of crawl the code, and it'll look for your require calls and probably import calls. And we'll check to see, are there any packages that you have installed that you're not actually calling from your application code? And so if it does, it'll then list them. So great tool. It's really useful in a complex code base where a lot of refactors happen. It's not necessarily 100% correct if you have any peer dependencies. It won't spot those, or you get a false negative. But otherwise, it's a good way to find packages that you should be able to safely uninstall. Another tip is to not install or not check in the node modules directory into the repository. You've probably heard this a bunch of times, but sort of some of the caveats with this is perhaps you're doing your development on a Mac OS machine. Maybe even you're using a different architecture like the M1 Atom or whatever it is. But ultimately, at the end of the day, you're probably deploying your application to an x86 Linux server. So either if you do end up having any native modules, which maybe you don't now, but maybe will in the future, if you're checking in those modules or the extracted packages into your Git repository and then you publish them, you can end up with issues in production. And also, ideally, you would never deploy dev dependencies to production. Does anybody do it knowingly? No shameful hands? OK. So, these dev dependencies, of course, the normal dependencies themselves also can add up to be pretty large. You can end up with, for example, Docker containers that are like a gigabyte in size. I've certainly encountered those as well. And so a lot of times, the dev dependencies are some of the biggest contributors to that. especially if you're downloading it used to be the Phantom.js binary. I worked at a company where we deploy that, and I think it was a few hundred megabytes, and just would slow down deploys. Best practices with regards to requiring packages. If you are still in a code base that you require, you should always specify the file extensions. That's going to get rid of some of this ambiguity. It can make it so it'll help with some of the refactors. If you're requiring a foo.json and then you add a foo.js, your code is just going to change. And you don't really want your code changing just because a file outside of that module you're working on happened to change. And it also used to help with code completion. I'm pretty sure VS Code is pretty smart now with determining which file to load. Never required a transitive dependency, and so any package that's not in your package JSON, just do not require it. The reason for that is, the reason why it works is due to the hoisting of the packages. So maybe you're requiring a file that happens to be hoisted to the root. Well, within your application code, you can only require packages that happen to be in that inside the top level node modules directory. And so as you install files in the future, that tree can shift, packages sort of move around, and so a transitive package that's in the root today might not necessarily be there tomorrow. Another fun thing is that the Instanceof operator is going to break if you install packages at different locations in the file system. And so even if you have the QS version 1.2.3 installed in multiple places, even though it seems like it's the same package, if you have a class instance exported in one, and you try to check if it's an instance of a class in the other one, that check will fail. And then the behavior that will then sort of change, maybe if you're using pnpm and the de-duplication changes, you can actually have differences between the package managers that you use to install these packages. And so ways to get around that is you can just sort of rely on duck typing, which is where you just check to see if the object is shaped the way you would expect. Or you can use maybe symbol.has instance. There's sort of a few ways around that. And then as far as security concerns, try to use the fewest number of packages that you can. If you can, try to favor modules with fewer 0 dependencies. I personally wish npm.js had a big badge, like a 0 dep badge. I would certainly appreciate that. Also, maybe check to see if module owners have other modules or that they're popular, of course. Consult the npm ls before and after installing packages. It's always good to keep an eye on how large your modules directory is. And finally, malicious modules are a real threat. Typo squatting is an issue that does happen, and that means that somebody publishes, code that is evil and can break your application intentionally, and then they'll sort of get you to install it in your application. There was an issue with a Bitcoin wallet software a few years ago you might have heard of. A lot of people lost money. And typo squatting, that's where they sort of squat on a typo. So it used to be, I think, maybe an Express.js was a play on Express.js, and you get something you wouldn't want. All right, well, that's it for the talk. Feel free to follow me on Twitter. This presentation is available online. This book is available online. And a book I just published and actually just hit print a few days ago called Multi-Threaded JavaScript. That is also available online as well. Thanks.